Okay, so now let's look at a few examples of Adams-Bashforth methods. Okay, so let's look at the simplest case, which is the m equals to 1 case, right, which is actually a one-step method. Okay, and so let's just sort of draw this pictorially. Okay, so you have tk and you want to compute an approximation at tk plus 1, right? This is f at k, right? And the point, of course, with the one-step, with the m equals 1 case, is that the only data you're taking advantage of is the fk it's like at that point. So the only thing you can do, obviously, is to have a constant approximation of fk, right? So the point then is that the integral from tk to tk plus 1 of, it's like this polynomial of degree 0 in S ds, right? So this P0 of S is basically just f at k, right? So this is just going to be equal to h, which is the difference between tk and tk plus 1 times f at k. Okay, so you end up getting a method which says yk plus 1 is equal to yk plus h of f at k, right? And h of f of k is just f at tk yk. So this, of course, is nothing more than the usual Euler method, right? So the m equals to 1 Adams-Bashforth method is just the forward Euler method. Okay. All right, so that's not so hard. Okay, so let's look at one more. So let's look at m equals to 2. Okay, so now m equals to 2, we have the solution at tk and tk minus 1, and we want to find the solution at tk plus 1. So let's say this is f at k, this is f at k minus 1. All right, so I can sort of now construct this linear interpolant, right, to give me this. All right, and I want to compute this integral here. All right, so again, you can convince yourself that if you look at this polynomial of degree 1, right, I mean, I can write down the Lagrange polynomials associated with this, but I can sort of see what it's going to be, right? I want to find this area. All right, so this area, so let me just look at the area of this block here, right? The integral from tk to tk plus 1 of p1 of s ds, right, is equal to h times fk, plus it's like the area of this triangle, and the area of this triangle is equal to the area of the triangle, right? This little triangle is just half h over 2 times fk plus fk so h over 2 of fk minus 1, right? Okay, so so that's going to be 3 over 2 h fk minus h over 2 fk minus 1. Okay, so once you have that, then you get the two sort of step Adams-Bashforth method, which says that yk plus 1 is equal to yk plus h times 3 over 2 f at tk yk minus 1/2 f at tk minus 1 yk minus 1. Okay, all right, so this is the two-step Adams-Bashforth method. Okay, and I should say that the Adams methods are what are called explicit, which is to say that if you look at the right-hand side, which you are being asked to evaluate, it doesn't require you to solve any equation, right? Everything on the right-hand side you already know, so you just have to evaluate that in order to find the solution at the new time. The same thing here, everything on the right-hand side involves times and solutions which you already have, so you can just evaluate that in order to compute y at k plus 1, okay? So what we're going to see next are what are called implicit methods, in particular what are called the Adams-Molten methods, where you have an equation where, for example, y at k plus 1 shows up on both the left and right hand sides. And so you might ask, well, why would you want to do this? And one possible reason to do this is to get a higher order method. Okay, so for example, if you have m equals to 1, right, so in the Adams-Bashforth method, we've just used that one point fk in order to compute the approximation of the integral of f along the solution. But you could have easily have said, well, okay, I know fk, and let's pretend I know f at k plus 1 as well. And then that obviously gives me a way to construct a better approximation of the integral, right? But what will happen then is that you'll get a method where yk plus 1 shows up both on the left as well as the right-hand side, okay? But you would have the benefit then of having a higher order, but at the cost of having the method be implicit because yk plus 1 shows up on the left and right, and so you have to solve some sort of equation in order to compute yk plus 1. And so that's the next thing which we're going to talk about, are these Adams-Molten methods, which are these kind of implicit methods. So let me stop here.